actually done that, and I've got the circuit drawn with the values in it. So you can just enter the values. So there was the circuit. There's the values. Now, in this one, those are text boxes, and you can type the values in. Right? So that's what I'm expecting you to do. So type those values in, please. So the value in black is the reading on the ammeter. And you should be able to see here that the 2 kilo ohm resistor had 4.5 milliamps of current flowing through it. Now, how would you write 4.5 milliamps in scientific notation? 4.5 times 10 to the minus 3. Have you written it down? Oh, okay, it's on. And the 3 kilo ohm resistor has 3 milliamps. So I'll come to you in a second, Mo. So was our suspicion correct? The smallest resistor had the biggest current. Yeah? Now, what's this business I've done here in red? Well, we'll talk about that in a minute. What's 3 times 1.5? And what's 2 times 1.5? 3. Now, what the heck is 1.5? Which current? Where? No, it's not. 7.5. Okay. No, we'll come to that in a minute. So, look. Yes? Yes, please. So I want you to type those in. So can you see that the ratio here is the inverse ratio of the resistances? Okay. This is 3 times a certain value, and this is 2 times a certain value. So the ratio, so observation here, I've written it down, and you can write this down, please. What's the observation? The higher resistance has the lower current. Okay, well, that was easy. But the total current is the sum of the parallel combinations. Can you see that? What's 4.5 plus 3? 7.5. No, I don't know how you get 1.5. I'm just doing it as a ratio. So I don't know how you get 1.5 from 7.5. Maybe divide it by 6. Divide by 5. You're thinking you divide by 5. Try it. Does it? Okay. So if you divide this current here by the total resistance, you get 1.5. So that's our observations. Observations is the biggest resistance is the smallest current. The 2 currents, they add up to the total current, and the current divides in the inverse ratio of the resistances.
Right, so what calculator do that? I have to use a formula.
There's a couple of formulas we can use. So I'll show you this. You can just do the inverse ratio to be
So where's the 1.5 coming from?
so if you took the total current and times it by 2/3, and then you times it by 3/2. Yeah. No, it doesn't. It works 2/5. If you take the total current and times it by 2/5, you'll get. Okay. Now, sorry, chaps. Let's just get it right. So here we're saying the ratio of the currents is the inverse of the ratio of the resistances. Now I want to show you what that looks like in numbers. Okay. So look here. Here's the resistance ratio. The resistance ratio is 2:3. Do you agree? That's kilo ohms. What's the total resistance? It's 5. Now, 3/5, the current will be in the ratio 3/5 is to 2/5. 3/5 times the total gives you 4.5. That's the current through the 2 ohm resistor. 2/5 times the total gives you 3, which is the current through the 2 ohm resistor. Yes.
Why is it 2 is to 3 and then the other is 3 and 5 is 2 and 5?
Because it's the ratio over the total. The total resistance is, yeah, if you just add the 2 resistances, total is 5.
So like the 2 and 3 must switch over.
Yes, because the biggest resistance gets the smallest current.
Okay. So why are we doing it so complicated with ratios?
Okay, you don't have to do the ratio. I'm just showing you the ratios because some guys like to work with the ratio. And I'm just proving to you that it's the inverse ratio. Okay. But you don't have to use ratios. You could just use Ohm's law at the bottom, which is much easier. Which is the current.
So the resistance to the 2 and the 3.
And the current is the 4.5 and the 3. Right? You don't need the 7.5.
So, but you times them by 7.5.
You know, for the ratio.
There is a way to get the 7.5. Obviously, I've told it to you in this example.
So
In an exam, we will give you some of the values.
you get the current, so you
Yeah.
seven currents you had to get.
That's correct. Yes. Yes. Okay, you can't. Well, there is a way to work it out. But so there is a way to work out the 7.5. Let me show you. I don't think I've showed you here. Let me show you quickly. There is a way to work out the 7.5. What is the total parallel resistance going to be? 6/5 or 5/6? Watch here. 1/R parallel is going to be equal to 1/R1. Do it like this. Let's do it like this. Insert shape. So 1 divided by R parallel equals 1/R1 plus 1/R2. You agree with that? Gentlemen? Agree? Good. Now, doesn't that mean that that's going to be equal to 1/3 plus 1/2, right? And isn't that going to be equal to, and those are milliohms, eh? Those are kilo ohms. What's 1/3 plus 1/2? Isn't that going to be 5/6? So how much is R parallel going to be? Which is how much? 1 point? No. 1.25, is it? Can I trust you? $1.2. Okay. So I'll believe the man with the calculator. Insert symbol ohms. Right, 1.2 ohms. Now, haven't you heard of Ohm's law? I is equal to. Now, if we're talking about the whole circuit, what's the voltage in the whole circuit? What's the resistance in the whole circuit? What is 9 divided by 1.2? Let me do quick mental arithmetic. I think it's equal to. Happy? No, you can put the smaller one first. That makes no difference. Yeah, a half plus a third is the same as a third plus a half. Yeah, that's right. All right. Where would we be without maths, eh? Still in the dark. We'd still be in the dark. Sure.
So you're going for a surf today?
Sorry?
You're going for a surf today?
No, my pumpy's broken. Believe it or not.
When our surf club going on again?
Sorry?
When our surf club going on again?
Surf club doesn't work, only works 2 and 3, term 2 and 3. Chaps, have I convinced you that those numbers are correct? Right.
So why is it?
It just is. It's got to do with the value. With
So if you wrote it as.
so, hang on a minute. So it's milliamps and kilo ohms. If it wasn't kilo ohms, it would be amps. Yeah. Yes.
If you wrote it as 3 milliamps, that'd be right. Yeah, right.
Yeah, that's fine. We have got the 9 from. Good question. Yeah. 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 No, don't be sorry. Fine. Don't be sorry. That's fine. No problem. Can we move? Okay. So that's simple little circuit, but it can get quite complicated. Do you agree? Right. So genius, the art of genius lies in making the complex simple. The art of genius. If you can make the complex stuff simple, then you're getting somewhere. Somebody just noticing my friend over there. How many of you have been nominated to positions of leadership in the school? Only you. Only you.
Yeah, I'm not.
All right, we'll see. So watch. Gentlemen, this was the summary that we did yesterday. So that's a little summary about parallel resistors. Here we've got, just don't know why I've done this again, because we actually did this yesterday. Didn't we do a summary there? Yeah, so that's the same summary. So actually there's nothing on this slide that we need to do new, right? Because we did that all yesterday. So what happens to the voltage in series circuit? The voltage? Now I've got a gap here for you to fill something in. I'm not going to tell you.
Stays up.
What happens to the voltage in series? Goes. Well, go back and look at this slide and see what you think about it.
Adds up.
Here we go. Okay, so this, if you look at them here, I've said it here in a different way. So you can look back at that one to give you an idea. Resistance in series. Current. Here we go. Write it down. Well done. You'll remember that for longer because you figured it out. Not the same. So I told you yesterday how to think about voltage and current. I don't know if you were listening when I said that. What if you think about the current and the voltage? What is the voltage? What's the current?
The voltage is the power the current has. Current is the flow rate of the electrons in the.
What did I say? Energy. Energy. Voltage is energy. Current is the amount of charge. Okay, so parallel circuits. Current does what? Adds up. Resistance. As you add more resistance, what happens? Doesn't add up. Decreases.
Yeah. Also written down.
And the voltage? Parallel voltage? The same. So in series, the current's the same. In parallel, the voltage is the same. All right. So that's yeah. Resistance decreases. As you add more resistance in parallel, your total resistance decreases. All right. So those are the little things that you've got to try and remember, because that's going to snooker you when you come to do your questions. All right. Very often you're going to be working at some place in the circuit and you're going to think, what's the current here? But we told you the current somewhere else, and this is also series bit, and now you must remember that it's the same. Okay. So this is just this business about, there's nothing for you to pull out here. It's just about the total resistance going down when you add resistance in parallel. And I'm just explaining it's because you're adding another route to the current. So while some current is going through this one, other current can go through this one. So the total resistance gone through by all the current is less. Right. And also here I'm showing you that you mustn't forget to invert this thing at the end. Okay. Okay, now let's talk about this. Electric current in a conductor. All right. So here I'm going to do a little animation for you. So what is electric current?
The electrons.
Electrons. Electrons are the only things that can move in the wire. Okay, atoms can't move, and that's all you've got with atoms and electrons. So now let's say I'm an electron in the wire, right? Or like if you look at this, this is a blow up of a piece of wire, and you might remember metallic bonding. So what's going on in metallic bonding again? Tell me. Delocalized. Why are they delocalized? Why are they not? The metals don't hold on to them very strongly. The metals are weak. They're pathetic. Okay. That's what some people think men are. But we know better. But metals are weak, right? They don't hold on to electrons very strongly. So the electrons can go walkabout. Now you put a strong positive charge here and a strong negative charge here. And this electron smells that strong positive charge. And he wants to go there. But can he go there if there's no space? No. Okay, so now let's pretend there's a space there. So I'm an electron, and I smell there's a big positive charge over there, so I get attracted, and there's a space there. So can I move it?
Yeah.
So I move there. Where's the space?
There.
So what should happen? That electron moves from there to there. Space. Actually, the space doesn't move. Space gets moved. Quite a nice thing to think about. Right? The space gets moved because the electron moves. Space has got no choice in the matter. I like this. Now, this electron can smell that positive charge as well, and now there's a space there, so he can move. Which means the space has to move there. And now that electron can smell that space and that positive charge. So he moves there, and the space moves there. So which way are the electrons moving? Towards the positive from the negative. Which way are the spaces moving? Towards the negative. What's in the spaces? Nothing. Nothing's in the space. That's why it's a space.
That one you.
So what's in space? Nothing.
That one negative.
Is that why negatives are ground?
Like far back, you have the ground, then you have the positive.
No, it's not. It's not. I'll tell you why in a minute. I'll come to you in a second. So listen to this. When we talk about electric current, what you're going to see is they're going to say, okay, conventional current is the movement of charge. Now, they're not going to go like this charge. They're going to say, in the textbook, you'll see it. Conventional current is the movement of charge from positive to negative in the circuit. Are there any charges in a circuit that moves from positive to negative? No. So what are we talking about when we refer to conventional current? We're talking about nothing. Little spaces of nothing. We're talking nonsense, actually. But remember, I've said to you, as long as you know you're talking nonsense, it's
Okay.
fine. Yes. I actually don't know. I suspect what happened was they came up with all these conventions, thinking that the movement was from positive to negative, and then they found out they were wrong. So rather than changing all the conventions that they've already set up, they just said, okay, we'll just say this is conventional code. And we know we're talking nonsense, it's fine. Yes.
So when electron moves, then all the other electrons are different.
So, yeah, so look, I've made this simplistic. Okay. I've got to be honest with you, it's probably a lot more complicated than this in reality. Because remember I said to you yesterday about how does this electron know that that one's moving? Now, one of the ways you could have said is if all the electrons are touching, right? Then as soon as this one moves, instantaneously they can all feel the bump, but they're not touching. So how does this one on that side of the circuit know that you switched on the switch? It's electric field. Now, what's that? We don't know. We actually don't. I mean, if we don't know what a magnetic field is, if we don't know what a magnetic field is, we've got zero chance of knowing what an electric field is. Now, so look, when I say nobody knows, some high-level physicist somewhere might have a theory about what it is. But whether his theory is correct is another story. And secondly, does he actually understand what he's saying? I personally think that there are many things, actually, that are beyond our capacity to know. I've got no problem with that. My brain is finite. Why should a finite brain be able to fully contemplate an infinite universe? I don't see any reason why a finite object should be able to fully comprehend an infinite object. And as far as we can see, the universe is infinite. So why should I expect that my finite brain can fully comprehend it? To me, that's not logical. So I've got no problem with things I can't understand. There's lots of things I can't understand, and I just accept it. Questions? Yes, go. Yes. So, yeah, look, you're going to learn next year exactly what's happening in the battery. So it's a bit more complicated than that, but it's kind of like it. Yes.
Does that have nothing to do with why you ground negative?
No. So the reason you ground a car negative, they just chose one of them. They said, okay, this is going to be the ground. And it's just to shorten the wires. So you don't have to have wires coming all everywhere. You just connect this to the car body and then connect anything to the car body and it's connected to it. Yeah, no, it's just a convenience thing. Is it lunchtime yet? Okay, I can talk forever about electricity. I love it. So if you want to stay, we'll carry on. Yes, John. Next year you're going to do it. We'll see it's chemical reactions. And this material actually it's all used up onto it. Yeah. Right on. Thank you, gentlemen. Great day.